Okay, so we want to derive the curve, the equation of the curve of the, the normal bell-shaped function. And that's from negative infinity to positive infinity. Uh, and so the situation here is, okay, we know we have a mean in the middle, and we're always comparing things to the mean. So, we have some x value in here, and we want to know what's the probability of being this distance uh, from the mean. And there are really two things here. This line is one thing, that's the probability density function, and then the area under it is the integral, and that's the cumulative density function. And basically what we're looking at is, once we have the probability density function and we take the integral, then we're looking at areas. And so we're trying to figure out what's the probability of having an x somewhere in here. Or, or it might even be all the way from here. There's lots of things that we can do. But the main thing to keep in mind here is distance. That's the function that we're going to derive is a function of distance. So the probability drops the farther away you are. And that's why we have, when we do the cumulative density function and take the area under it, well, it's a smaller probability because it has less area. But of course, the other factor is amount of area, because even though a point or a range of points may be farther away, if we make the area bigger, it makes the probability greater as well. So two things that come into play here are distance and area. And the way a lot of people think about this, from what I've seen so far, is to derive it. A good illustration is a dartboard. And the bullseye is the origin. And so people are throwing darts at the center, so there's going to be more here than there are out here. And so stronger probabilities come from being closer, smaller probabilities the farther away. And so if you kind of thought, okay, what's the probability of your dart landing in this slice of x? And so we'll call this delta x. What's the probability of your dart being in here? Well, we would need a probability function, we'll call it p of x, that would express the probability in terms of being farther and farther away, and giving a smaller probability with the greater distance. And so you could say, well, the probability of being in this slice, we could say that's the probability function, whatever it is, times the area that is that wide. Because obviously if we had a wider area, then we would have a greater probability of the dart landing in there, even no matter how far away it is. But then if you said, well, what's the probability of just being in this little square or rectangle? Now we're looking at a slice of y. So another delta y, and probability. And this would be the same formula in this case. It's doing the same thing. It's looking at how far away that y, section is away from the origin, and it's diminishing the probability as we get farther away. And so we've got an area of delta x times delta y, and we have our probability of x, probability of y. So we could write the probability as probability of x times the probability of y times delta x times delta y. And one thing we want to stress here are the assumptions that we make from the beginning. We assume that the x slice, where the dart ends with regard to the x-axis, is completely independent of where it lands with regard to the y-axis. The y doesn't influence the x doesn't influence the y. Another thing that we assume is we're only concerned with distance, not orientation. So if you had, this little square someplace else, but it's at the same distance, the probability is going to be the same. So we don't care about the orientation as far as the circular motion. Okay, so we've expressed this in terms of, okay, x distance and y distance. But what mathematicians do when they derive a formula is, at least one of the main strategies, is they find another way to express the same thing and they pit them against each other. And that just allows us to, to just do stuff and experiment and see what happens. Well, is there a way we could express the distance of this square from the origin in terms of, instead of xy distance, another distance? And certainly there is, because we have a direct distance, which we could call the radius. What if we just had a function that was a function of r, the radius, and then we're multiplying that by the distance? And that seems pretty logical, that you could express the scenario this way or this way. Okay, again, keep in mind before we move on, if we were at the same distance away but we made the area bigger, we have a greater probability. If we kept the area the same but we brought it closer, we would also have a greater probability. So two ways to create a greater probability. Okay, so this is the foundation. This is going to be our kickoff. And the first thing I'm going to do is divide both sides by the area. So really, we're kind of making the area irrelevant to start with. And it kind of makes sense because we're deriving this curve, not the area under it. So we really are, looking for a function that is a function of distance. Okay, so this is what we have. Two different ways of expressing probability in terms of distance, and that's with the x and y working together, or just the radius. Okay, so continuing on from here, keep in mind that we have rectangular coordinates and polar coordinates, and we're going to be using both those here. And remember, with radius, when we're expressing an area with regard to radius, then we have our radius and we have an angle, theta. So just like x needs y to express an area in one way, r needs theta to express an area in another way. And one thing we're going to do is we're going to differentiate both sides with regard to theta. You may say, well, why do we do that? Well, again, it comes back to when mathematicians derive a formula, they don't usually just go directly there. They experiment, throw stuff against the wall and see what sticks, so to speak. And so we kind of know theta has got some relevance in this scenario, so what if we just inject it into here? And so remember, we can differentiate both sides with respect to anything we want, whether or not it's relevant. So we're going to choose to do that with theta, and actually it will be relevant. So we're going to use the product rule here, and so we're going to leave that alone, and then we're going to have a change in the y function over a change in theta. Now we're going to leave the y function alone, and we're going to have a change in probability of x with regard to theta. And if you think about it, if theta changes, it does affect the length of x and y. If you have a different angle here, then your x and your y are going to be different than if they were out here. So theta does influence x and y, but theta does not influence radius. This radius could be anywhere, and the length of it is not affected by theta. So there is no slope other than 0 between these. So when we differentiate radius with respect to theta, we just get 0. Okay, now let's write this out with the chain rule to make a little more sense, because there's a whole function in here. We have probability and y and theta. So let's write the whole thing out. So d probability dy times dy y over a change in theta. Same thing here. So dp dx times dx d theta. And now we're going to make use of these identities. X equals r cosine theta, so we know dx d theta would be r, actually would be negative r sine theta, and then y equals r sine theta, and so dy d theta would be r cosine theta. So we're just going to use this to make substitutions in here, and so we can leave this alone, but dy d theta, well, that's just this, r cosine theta. But r cosine theta is actually x, so we can just substitute there. Same thing here. Okay, dx d theta, well, that's negative r sine theta. So actually that would be, so that's going to make this negative, so it's going to equal negative y. So we could put the negative here and make that y. And last thing we're going to do is just add this to both sides. So now we have two equal things. And let's see, actually one last thing, let me get a different color here. I want to have x stuff on one side and y stuff on the other side. I've got stuff mixed here, so what I'm going to do is I'm going to keep the dp dy over here and the dp dx over here, and I'm going to divide this x and px over here, p of x, and I'm going to divide the y and the p of y over to here. Okay, so on the next slide we're going to start with this. Okay, so now we, as we look at this, we see something interesting, because according to this, for any value of y, this side is going to be valued, the value of this side is going to be equal to the value of this side for any value of x. So this is always the same thing. Well, actually, to reason it out, how could this always be equal to this for any value of x or y? And the answer to that is, well, they must always equal the same thing. This must be a constant, this must be a constant. These must be equal to some constant. So now what I'm going to do, since we really only want x in here, we don't want y, is we're just going to dump everything on the left and we're going to take this. And this is a differential equation. So hopefully you're familiar with those. We're just gonna take this and do the differential equation, and we're gonna get a basic function that we can build on from there. Okay, so what I'm gonna do, I want to keep the 1 over p of x on this side with the dp, and I want the dx and the x over on this side. So let's see. So we would have 1 over p of x dp equals c1 times x times d of x. And so now this is a separable differential equation. So we've separated the stuff by sides. And so now we're just going to take the integral of both sides. And so this is going to become natural log of p of x. We don't need to do absolute value because we wouldn't have a negative probability anyway. And let's see here, we'd have that, and then we'd have another unknown. So we'll call that C2. Okay, and then if we exponentiate both sides, we're going to get p of x equals, and so we have e to this whole exponent. But we know we can write this as this way because these are same bases, and if we combine same bases by multiplication, we add the exponents. And then notice that this here, e is a constant, c2 is a constant, so that's just some constant. So we're going to call that a, and we're going to put it in front. And now we see our basic foundational raw function forming up here. And one last thing, though, that we're going to do before we go to the next slide. Remember, we're looking for this curve. It has to drop the greater the distance. But this, if C1 is positive, this is going to be growing. And that's certainly not what we want it to do. So we're going to have to make this drop as x goes to infinity or negative infinity. That's going to make the line y equals 0 asymptotic. And that will happen if we make sure that C1 is negative. So let's just do this. Let's say C1 equals negative k. So I'm just going to switch that right here. So negative k over 2. And this is going to be the basic function that we're going to build on from here. Okay, well now we need to figure out some way to get an expression for a and then for k. So let's talk about a. How can we figure out what it is? And that's where we use constraints that we know have to happen to force things to manifest themselves. And so if you think about what we're doing here, we're looking for the equation of this curve. That's the PDF. The CDF, the cumulative density function, is the area under it. And we know that since this is for probabilities, we know that you can't have a probability greater than 1, and area is probability. So that means that from negative infinity to positive infinity, the integral of this function has to equal 1. And so we have to make that happen. Yeah, that's pretty sloppy. So the integral must equal 1. Okay, one thing we're going to do is, we know this is symmetrical, so really we should just take the integral from 0. That'll make it simpler. Which means we need to multiply the whole thing by 2. And then I'm going to divide 2a off. And now we just need to do this integral. So we need to not forget where we came from, what we're doing here. We're trying to figure out what a is. Okay, this integral does not have a good direct way to do it. If you try u substitution, integration by parts, trig substitution, whatever, it's not going to work. So some clever person, I don't know who, thought up a maneuver so that we could get this done. And here's what it looks like. We're going to square both sides. And what I'm going to do is I'm going to write this as, I'm just going to put it beside itself. Okay, so why did I stick a y back in here? We got rid of y's before, now we're pulling it back. Well, if you think about it, it's justified because it doesn't matter what the variable is. It doesn't change what the value of this is going to be. It's still going to be equal to this. But what that allows us to do is we're going to use polar coordinates. And that's going to get us around. See, our problem here is we have an x squared. If we had an x, then we could take the integral. But we don't. But it just so happens that when you do polar coordinates, you have that extra r in there, and that's going to give us an r squared and an r, and then we can do u substitution and no problem. So how do we do this? So basically we want to remember this thing, 1 over 4a squared. And once we figure out what this is, we're going to take this expression and pit it against this one and solve for a, and then we're going to know what a is. Okay, well, how do we do this? So let's take a break from this for a second and let's think about, okay, so just to show you, so that what I'm going to do here makes sense, I just want to go off to the side here and make a point. So if you had a double integral and you had a y and an x integral, and you have some function of y times some function of x, well, what you would say is, okay, first I need to do the inner integral, but when I do that, the f of x is just a constant with respect to y, so we could just move that out in front of the x integral. And then we would go ahead and do that x integral, and that would just be a number, and that number would be a constant with regard to the y integral. So we would just bring it out in front, and then the y integral, should have had a parenthesis there. I'm too much of a hurry here. Okay, so we see that this whole thing stuck together is equal to the two integrals separated by multiplication, and that's possible because this is multiplication, it's not a sum. And so what we're actually going to do is we're going to take these two things sitting side by side and we're going to smush them together. So we're going from this to this. Okay, so back to what we were doing here. Okay, so what we're going to do now is we know that this, well, let's see. Let me take, so the e here, we know we can write this. Let me get a different color. We know this whole thing here. Can be written as this. It can be combined just like we did before, and you know exponent rules, I'm sure. Okay, so that's what this thing is, and this thing we're going to call x squared plus y squared r squared because we're going to change to polar coordinates now. So we're going to have e to this stuff, and hopefully you know changing to polar coordinates, dx dy changes to r dr d theta. And of course, now we need to change the bounds of integration. And so let's think about what was going on here. We have x from 0 to infinity and y from 0 to infinity. So if we think about that, so x is going from here to here. We're taking an infinite area. Y is going from here to here, and we're taking this infinite area of the first quadrant. Well, how would we cover the same area with polar coordinates? Well, we would have a radius and we would have an angle, theta. And the radius would have to go from 0 to infinity. And the angle would have to go from 0 to pi over 2. So on the next slide, we're going to take the integral of this new, we're just going to do it. Okay, continuing on here. So I think what I'm going to do is let's just take this first integral off to the side. Okay, and my R's look like V's there. We're going to do a U substitution. And when I do a U substitution, I like to do it like this. Then I can see my R's cancel out, and I'm going to have e to the u du, and I'm going to have a negative 1 over k. So, bounds of integration. Okay, if r is 0, u is 0. If r is infinity, u is going to be negative infinity. And I know technically I'm supposed to write this as a limit rather than just plugging in infinity, but I'm going to be lazy and just plug it in directly, so you can sue me. Okay, so the integral of e to the u is e to the u, so we can go ahead and plug in directly. So e to the negative infinity, that's going to be 0, and e to the 0 is going to be 1, so negative 1. So negative 1 times negative 1 over k is just 1 over k. And so we figured out this whole inside thing is 1 over k. Okay, so theta, so this is just going to be the integral of 1, so that's just going to be theta. And then we're going to plug pi over 2 into theta and 0. So this is going to be equal to pi over 2k, which we know is equal to this. And if we solve for a, we're going to get a is equal to and this was what we wanted. Now we can take this back to our original function and substitute it for a. Okay, so we had this and we figured out that a is this, and so I've simply rewritten it with a substituted for. Now we need to deal with k, and we do have constraints left that we haven't dealt with because we have to get the mean and the variance involved, because that's what this is all about. And so we need to, let's think about the mean of this expression. So our standard formula for expected value, the mean, is simply negative infinity to pi. Well, we're doing an integral because this is continuous, but we know that we would be summing up all of the x's all the possible x's times the probability of them happening. And so in this case, we would have this, and we could go ahead and do this, and you would see that the mean is 0. Or you could just think about the fact that this is actually an odd function because we have an x squared and we have an x, and if you plugged in a negative x, you would get the same thing as before, except it would just all be negative. And so if you think about an odd function and taking the integral of it, so, you know, say it's something like that, and we're taking the area from negative infinity to positive infinity, well, it's a negative area and a positive area. They're just going to cancel to 0, and so our mean is actually 0. Okay, now thinking about the variance. So our standard formula for variance is we just sum up all the possible square differences of the mean with the probability of that happening. And in this case, it would be an integral since, you know, again, it's continuous, not discrete. But really, it simplifies it some since we know the mean is 0. So we're just going to have x squared and then p of x. So we're going to have, keep that out front, and then we'll have the integral here, and this will give us the variance. And so that's the next thing we're going to do, and it's going to give us a way to see what k is. And we're actually going to see that k is inversely proportional to the variance. Okay, so we need to do this integral now, and actually, since this is symmetric, again, we can change this to 0 and multiply this by 2. And what I want to do, let's just leave the constant part in front alone, and let's just do this whole thing separately. And then we'll come back and get this. I wrote x squared as x times x because we're going to do we're going to integrate with, can't think of the name of it, integration by parts. Had to pause and try to think what the term of this was, the name of this. Integration by parts, and I've got this written here because I like to be looking at it whenever I do it, and so we need a u, and we're going to make u x, so du is going to be dx, and all of this is going to be dv. And v is going to be, and I'm just going to write it, I'm not going to take time to calculate it in front of you. I'm sure you know how to do this. Okay, and so when we do this, we're going to get u times v, so that's just going to be this times this. So I'm going to set the u on top, sorry, the x on top of the k. And that's, of course, integrating from 0 to infinity. And then we have to do minus the integral of v du. And so v, that's negative 1k. Let's put that in front. Okay, so let's think about what this is. So this first part here, And again, I know I should have written this as a limit, but I'm just being lazy, so I'm just plugging in directly. But if you plug in infinity here for x, you're going to get e to the negative infinity, which is going to be 0, and it's going to kill this. And if you plug in 0 here, it's going to turn into 0 and kill this. So this whole thing goes away. Okay, so actually, let's go ahead and continue out here. So we're going to have 1 over k. This thing here, we already did. Okay, a little flashback here. Back when we squared the function and then we ended up squaring this. Okay, if you look at this part here, not counting the 1 over k, but just this part here, that was equal to the square root of this. So this thing here is equal to 1 over 2a, and 1 over 2a turned out to be equal to all this. So we're down to this. Okay, I'm going to have to make some room. Okay, so going back to here, what we're going to have is that the integral is equal to, so let's get this involved again now. So I think I'll just make one big fraction here. So that's this, and then we come over here and we have 1 over k, 1 over 2, and we have 2 pi and root 2 pi and root k. And if we just cancel everything, we get 1 over k. And this is what we were after. So 1 over k equals the variance, and so we can say k equals 1 over the variance. And this is now what we're going to use to go back and substitute for k in our function. Okay, so we're finally done. We just took the k's and substituted them using this identity here, and now we have things in terms of the variance, and we're almost there, except one last thing that we wanted to be able to do was, what if mu isn't 0? Well, we need to be able to shift this thing horizontally. And so if you just make this little adjustment here, then whatever mu you put in there, this curve here will center over that mean. And you may notice that this is a z-score, and so we're used to taking a z-score and going to either a z-table or software, but with this you can plug your z-score into this and take the integral of it, and it will give you the probability instead of the table. This is your probability density function, and the cumulative density function is just the integral of this, and it's giving us this, and it's given us an area up to some certain x. So you would integrate this normally from negative infinity up to some value of x, and it will give you this area, which will give you a probability. And so that's how it's done by hand. There is a downside. This was disappointing to me when I found out about it. Taking the integral of this is impossible directly. It is not. This is not the derivative of some elementary function of which you could take the integral here and go back to the function. And so plugging in a z-score and taking the integral is just not as simple as it sounds. The only way to do this integral is with approximation techniques, usually turning e into a power series and then integrating term by term and doing a bunch of terms so you're as accurate as possible. But it's a real pain in the neck. So I remember that was disappointing to me to find out that it wasn't as easy as just plugging in a z-score, take the integral, boom, 1 minute later you have your probability, and now you don't have to use z-tables or software. That's the kind of the bummer thing in all this. But anyway, you might as well know that now. But anyway, we did what we wanted to do. We have derived the normal probability density function. Scary, horrible looking formula. The first time I saw it, it made me very uneasy because I can't stand seeing formulas that I don't understand. And I felt better when I learned how to derive it. And now, so you can show this formula to your friends and tell them you understand it, and maybe they'll think you're really smart.